If you've been following the electric vehicle market, you've probably heard a lot about
Cobalt.
Cobalt.
the reason cobalt's been getting so much attention is because it's one of the metals used to make lithium-ion batteries, which power everything from laptops and cell phones to electric vehicles. The amount of different metals found in an EV battery can vary depending on the battery type and car model, but a typical lithium-ion battery pack may contain around 14 kilograms of cobalt. Cobalt has been a popular choice for batteries because the metal increases battery life and energy density, which in the case of EVs means range, by keeping the battery structure stable as the battery is continuously charged and discharged. But cobalt, which is usually extracted as a byproduct of nickel and copper mining, is one of the most expensive materials in a battery. While battery prices have fallen 89% between 2010 and 2020, they still make up about 30% of the total cost of an electric vehicle.
For a typical vehicle with say an 80 kilowatt hour battery today, we estimate that cobalt content alone costs around $800 in that battery, so that's not insignificant.
For mass electrification to happen, there are a lot of sentiments that cobalt needs to be eliminated or reduced to the bare minimum.
Cobalt extraction is also linked to human rights abuses and child labor. These are some of the reasons why battery manufacturers like Samsung and Panasonic, and car makers like Tesla and VW, along with a number of startups, are working to eliminate cobalt completely. Elon Musk has been talking about removing cobalt from Tesla's batteries since 2018, and some of the company's China-made vehicles are already using cobalt-free technology. But although there are a number of different cobalt-free technologies being tested, each has presented its own challenges.
Cobalt helps to prevent battery fires. So if you eliminate it, you have to replace it with something else that maintains safety and longevity.
EV sales worldwide are expected to skyrocket from 3 million in 2020 to 66 million in 2040. And with increased demand for EVs, demand for raw battery materials like cobalt is expected to outstrip supply.
Comparing demand and supply for cobalt, there is, geologically speaking, enough raw material in the Earth's crust. Same with lithium, same with nickel, same with manganese. It's just that the production and the processing of that material, just like all the other materials, is nowhere near the level that it needs to be to sustain the level of demand.
One way to ease demand for new cobalt mining is by recycling the cobalt found in old batteries. Companies like Redwood Materials in Nevada and Canada-based Li-Cycle have emerged to do this. But some types of recycling have downfalls.
Currently, cobalt is recycled, but the process in which it is recycled is very environmentally unfriendly. You take old batteries and you smelt them at temperatures higher than 1000 C, and you can extract the cobalt back out of it. The reason that is done is because of how expensive cobalt is.
For the past 4 years, the average cost of cobalt was more than the cost of all the other battery metals put together. The price of cobalt has also historically been very volatile. Part of this volatility may be due to the fact that cobalt is usually produced as a byproduct of nickel and copper mining, and therefore tied to the demand and price fluctuations of those metals. The mining and refining of cobalt is also geographically limited.
The majority of the world's battery-grade cobalt reserves are located in the Democratic Republic of Congo, where the mining of cobalt is associated with human rights abuses and child labor and so on.
Chinese investors control about 70% of Congo's mining sector. China also has over 80% control of the cobalt refining industry, where the raw material is turned into commercial-grade cobalt metal suitable for use in EVs. In light of the US-China trade war, cobalt supply is in a precarious position for US manufacturers.
The reason China has really dominated is they've quite embraced the lithium-ion battery revolution.
To understand the importance of cobalt in batteries, we have to talk about battery chemistry. A typical lithium-ion battery has 3 main components. The negative end is known as the anode, and the positive end, the cathode. The 2 electrodes are separated by the electrolyte, a substance that conducts an electric current. The movement of positively charged lithium ions from the anode through the electrolyte and to the cathode creates free electrons, which travel through an external circuit and carry the electric current used to power a device. When a battery is charged, this chemical reaction is reversed. Different types of lithium-ion batteries are distinguished by the metals that make up the cathode. This is where cobalt is found. Today, the market is dominated by NMC batteries, whose cathodes contain nickel, manganese, and cobalt. Depending on the proportions of each metal in the cathode, which are represented by the numbers following the cathode names, you will get different properties in the battery. For instance, increasing the nickel in the cathode boosts energy density and therefore range, but also makes batteries more unstable. That's because adding more nickel usually means decreasing the amount of cobalt, which prevents cathode corrosion that can lead to battery fires. Battery and car manufacturers try to optimize battery chemistry on the parameters of cost, life cycle, safety, and range. Some cobalt-free batteries do already exist, but there are trade-offs.
There is already a viable cobalt-free battery, and that is lithium iron phosphate, or LFP. But the main downside of LFP is low energy density and therefore driving range.
You can see lithium iron phosphate right now in buses, so things that don't need to go that far and they have a regular routine. But as consumers, we want cars that can compete on a one-to-one footing with the internal combustion engine. And those cathodes that don't contain cobalt right now are not able to deliver that.
The production of lithium iron phosphate, or LFP batteries, is dominated by Chinese companies like BYD and Contemporary Amprex Technology Limited, or CATL. One reason is an old licensing agreement that allowed Chinese manufacturers to make LFP batteries without having to pay an expensive fee to the patent owners as long as they sold the batteries within China. The last of these patents, which are owned by a Swiss-based consortium, expired in September of 2021 in Europe and are set to expire in 2022 in the US. This has opened the floodgates for major Western automakers to use iron-based battery chemistries.
American and European OEMs are adopting LFP in parallel to their high nickel batteries because it has great advantages over high nickel and cobalt-based batteries. Notably, it's a lot cheaper. The component materials are a lot more readily available and abundant than nickel and cobalt, and it has a longer longevity.
Lithium iron phosphate batteries are also generally considered very safe, since iron is a very stable element. Ford and Volkswagen have both said that they would offer vehicles with LFP batteries. Tesla already uses LFP batteries in the Model 3 and Model Y vehicles it manufactures in China, and the company says it will now expand use of LFP batteries to all of its entry-level Model 3 and Model Y vehicles. Previously, these cars used nickel cobalt aluminum oxide, or NCA batteries, which Tesla will continue to use in its long-range versions.
Our long-range vehicles use a nickel-based cathode, and we use nickel because nickel has higher energy density for our long-range vehicles. But for our standard range vehicles and for stationary storage, I think all of that will move to iron cathodes. So moving to an iron-based chemistry, which is sort of finally at the point where it's competitive on range when combined with an efficient powertrain. I think that will be the vast majority of batteries in the future will be iron-based.
Even Apple was reportedly in talks with Chinese LFP manufacturers to make batteries for its planned EV car project, though those talks seem to have been put on hold. In an effort to reduce US dependence on foreign countries, the US Department of Energy released a national blueprint in June to help guide investment to develop domestic lithium battery manufacturing and support further R&D. Among its goals, the blueprint calls for eliminating cobalt from lithium batteries by 2030. Two US-based startups, Sparks and TextPower, say that they can help, though the companies have yet to prove out their technologies in electric vehicles. Sparks was founded in 2019 by Sanjeev Malhotra, a former executive at the US Department of Energy. The Tennessee-based company has 15 employees and was born out of a partnership with the Department of Energy's Oak Ridge National Laboratory. Sparks says it's raised over $10 million in grants from the DOE, the California Energy Commission, and several early customers to bring its cobalt-free lithium-ion battery to the market.
That was one of the key motivation factors for starting Sparks, was to address the supply chain issues for lithium-ion batteries, predominantly for cobalt, and make US independent of any supply chain that is dependent on China.
Sparks is still in its testing phase. The company says it's initially focusing on supplying batteries for large transportation vehicles like buses and trucks, off-road vehicles like farming and factory equipment, and energy storage solutions. Sparks says it's also in talks with two auto manufacturers and will begin testing its batteries in their vehicles next year. Sparks' technology focuses on replacing the cobalt in its cathode, which also contains nickel and aluminum, with iron. The company says it's considered other metals but chose iron because it's cheap, widely available in the US, and chemically stable, making it safe to use. Malhotra says Sparks' battery cathode material, which the company calls NFA for nickel iron aluminum, improves upon iron-based cathode chemistries and those containing cobalt.
The energy density of the cell using our cobalt-free cathode is twice that of the LFP. And in terms of the cost, we're almost about 30% lower than that of LFPs. Yet at the same time, this cobalt-free cathode meets and exceeds the performance that you would see from a traditional cobalt-carrying cathode in terms of energy density, which is the energy that you can pack in a certain weight or a certain volume. It meets the life expectancy of a traditional lithium-ion battery. And in terms of cost, it's almost about 35 to 40% lower than the cost of your typical lithium-ion battery.
To create this NFA cathode material, Sparks has licensed 6 patents from Oak Ridge National Laboratory.
The primary focus of these 6 patents is on the design of the material that's used while eliminating cobalt and replacing it with iron. Secondly, the process to make the cobalt-free cathode a lot more stable. And then the third is the manufacturing process. So there is one patent that essentially reduces the time to manufacture, because the time to manufacture translates into cost.
Sparks says its cobalt-free batteries can be produced using the same equipment used to make conventional cobalt-containing batteries.
We're currently looking for about close to 2 million square foot, where we will be setting up the manufacturing for these 3 parts of the value chain: the cathode material, the electrode, and the cells. And essentially, we've identified a couple of scale-up partners, and through some strategic partnership, we are looking to have manufacturing for these 3 components starting next year.
Like Sparks, Houston-based TexPower was founded in 2019. The startup was spun out of research headed up by Armugam Manthiram at the University of Texas at Austin. In 2020, the research team published a paper in which they tested a cathode made of manganese, aluminum, and 89% nickel, and found that their cobalt-free material performed very well when compared to cobalt-containing cathodes.
We do not see any downside with the performance of our material without any cobalt compared to the performance of the material containing cobalt. The cycle life, as well as the how fast you can charge, discharge, and safety.
This cathode composition was the jump-off point for the material that TexPower is trying to commercialize.
We're commercializing our nickel manganese aluminum-based chemistry that's cobalt-free, higher in energy density than current lithium-ion battery cathodes, and operates stably and safely.
Globally, the most widely used cathode material today is NMC 622. This cathode is composed of 60% nickel and 20% each of manganese and cobalt. TexPower says it's able to increase the energy density of its cathode material by replacing cobalt with larger quantities of nickel. But increasing nickel in the cathode has traditionally come with its own challenges.
Nickel is highly reactive with the electrolyte, so cobalt is typically added to minimize the degradation of the cathode structure. And then other elements like manganese are added also to improve the thermal stability. So all these other elements that are added are typically added to make up for the deficiencies of nickel.
TexPower says that it's navigating this instability problem by adding aluminum and manganese, as well as a number of proprietary substances known as dopants. The result, the company says, is a cathode material that is 20% cheaper than the conventional NMC 622 cathodes. But producing this material is tricky.
Decreasing the cobalt in the material makes the production harder. It will also be difficult to get consistent properties from batch to batch. So the process TexPower is developing is to minimize that kind of concern, so that when you produce tons and tons of material, you will have consistent properties from one batch to another batch.
Whereas cobalt is generally easy to synthesize into a cathode material, getting the right reaction using nickel requires close monitoring and control over factors like temperature and oxygen flow and pressure. It took years for the team at UT Austin to fine-tune the production process of their nickel-manganese aluminum cathode material. TexPower will use the same process to produce its cathode material at scale.
Our production technique is immediately scalable. It's the same production technique that they use industrially. And so next year, we're building a production line for hundreds of kilos of material per year.
TexPower makes just the cathode material and plans to partner with other companies to produce battery cells.
We have a contract with the Department of Defense in conjunction with 24M, where they're producing a high energy cell with lithium metal anode and our highest energy cathode material. And we're reaching energy densities in excess of 500 watt hours per kilogram. That's around double current commercial lithium-ion batteries.
Still, Erickson says that it may be a while before Texpower's cathode materials are used in EVs, although it is in talks with a number of automakers.
The automakers have, several years of safety testing and things like that they'll go through before they'll put it into a commercial vehicle. But, as early as the end of 2023, we could have some prototypes in electric vehicles.
Although cobalt-free battery performance continues to improve, experts believe that the future EV battery market will consist of a number of different battery chemistries for different applications.
We calculate around 20% of the global battery electric vehicle market by 2030 being taken up by these new cobalt-free chemistries. We expect that the sort of entry-level low-cost vehicles, for example, the standard range model, Tesla Model 3, will be LFP or lithium iron phosphate, and then followed by these cobalt-free materials, which will account for most of the mainstream volume vehicles. And then at the top end of the range will be high nickel batteries, which will account for high performance, high range vehicles.
Other battery breakthroughs could help enhance cobalt-free chemistries. Car companies Hyundai and Kia announced they're working with US-based Factorial Energy to replace liquid electrolyte batteries with solid-state electrolyte batteries. This would give batteries an even longer range and added safety benefits.
With these cobalt-free batteries, they operate at higher voltage, and that's one reason why they are more susceptible to battery fires. With solid-state batteries, it's just like your solid-state hard drives. It's a solid electrolyte. It's able to withstand higher voltages. It can potentially deliver a higher driving range, which is what's the most important thing for a consumer, but also higher safety and faster charging times.
We just have received another grant from the California Energy Commission for next generation batteries, which is basically solid-state batteries using our cobalt-free cathode, which has the potential of doubling the energy density that we have today. So basically making it almost 4 times that of LFP.
Meanwhile, others are focused on improving the battery's form.
Certain companies like, for example, BYD, are attempting to offset the range disadvantages of LFP with certain things like what we call cell-to-pack technology, where we do away with splitting the battery pack into modules. We just have the entire battery pack as a number of cells together, and that gives you a better range advantage.
But whatever advancements we make, experts stress the technology needs to be widely accessible.
When you think of cobalt-free cathode chemistries, what we are hoping to have is batteries that are more accessible to all. That makes it easier for developing countries to adopt a lot of the technologies that we are trying to develop without fear for cost, without fear for performance. The Industrial Revolution left many people behind, but we cannot afford for this renewable energy revolution to leave anyone behind.